In this video, I want to continue talking about the example which we were speaking about before, which is whereby we've got some sort of population, and within that population there is a fixed proportion of individuals who have a disease, and then we take a sample from that population, and what we're trying to do is we're trying to do some sort of inference on the potential values which theta can take, which in Bayesian inference takes the form of the posterior distribution, the probability of theta given our data x. And we've already reasoned that we can just use our simple update formula here to work out the posterior density, and we know that our beta distribution, which governs our posterior, is equal to a plus x with its sort of first input, and its second parameter is going to be b plus n minus x. So that's going to be the posterior distribution, and so you can see it depends on a and b, but it also depends on the sample size as well as the number of individuals who actually have the disease. And you can see, because of the fact that n is normally quite big, this n here is going to come to dominate the distribution to some degree for any sort of large samples. And we spoke about the fact that essentially we can think about the posterior as sort of being part of the way between the likelihood and the prior. So if we specify a prior which is, as we said, quite incorrect here, so perhaps we had a prior which looks something like this, and then we actually have a very small proportion of individuals in our sample that actually have the disease, so our likelihood looks something like this, and note that the likelihood here is going to be actually quite a lot smaller than the prior, so this isn't necessarily drawn to scale, and our posterior, which is actually a correct probability distribution, is going to be somewhere between these two extremes. So our posterior might look something like this red line that I've drawn here, for example. So to be clear here, the posterior is some way between the likelihood and our prior distribution. But we can ask ourselves, well, exactly how far between the prior and the likelihood is it? And, well, how do we actually talk about that in the first place? Well, we have to, or one of the ways we can do that rather, is to talk about the mean of the posterior density. So we work out the expected value of theta given that we've received the data. And that's easy to do in this circumstance because we already know that the mean of a beta distribution, if a beta distribution has got a first parameter a and a second parameter b, we know that in that circumstance the mean of theta is equal to a over a plus b. Of course here our new a is this sort of a plus x and our new b is b plus n minus x, but we can still plug in our sort of new parameters into our formula, which gives us that the mean of the process is a plus x divided through by, in this case, just a plus b plus n, because the x is going to cancel with the minus x on the bottom here. So what we can do now is we can sort of split this up into two corresponding terms, one of them which is to do with the prior and one of them which is due to the likelihood in this example. So firstly what we do is we just split this up, so we get just a over a plus b plus n plus x over a plus b plus n. So all I've done is just separated this expression out here into its two corresponding individual fractions. Then what I'm going to do is I'm going to rewrite this first term here as a over a plus b, and note that that is actually, the way I've written that is the prior mean, times, well, I have to multiply it through by a plus b over a plus b plus n. And the reason I've done that is because the a plus b here is something that I've introduced, so I've got to multiply it through by a plus b on the top such that it cancels with the bottom. Okay, so that's the first term. The second term here, I'm going to do a very similar thing, except what I'm now going to do is I'm actually going to multiply this through by 1 over n. So I just get x over n times, then we've just got n over a plus b plus n. And note here that essentially what this first term is this is the maximum likelihood estimate of the value of theta. Whereas this term over here is the prior sort of mean or value of theta, which we would have prescribed before we actually carried out any sort of inference here. So what we can note is we can note that here the posterior mean is equal to the prior mean, mu prior, times some weighting function, which is a function of both a, b, and n, or all three of those things rather, and then we've got plus the mu of the sort of maximum likelihood estimate times some other weighting function of A, B, and N as well. And we can say how each of these weighting functions varies as we change A, B, and N. We can see here, if we begin with a sort of top expression here, that as I increase A and B here, then that's going to increase the sort of proportion which we prescribed to the prior. So it's going to be a positive function of both A and B, and as I increase N here, N is going to increase the denominator, so that's going to decrease the weight. So it's a negative function of N. And that makes sense, because as I get more data, I apply less weight to the prior. Let's now look at the second weighting function here, N over A plus B plus N. This is going to look pretty similar, except it's going to be sort of inverted. You can see here that as I increase A and B, that's just going to increase the denominator here, and hence it's a negative function of A and B. And that makes more sense, because as I increase A and B, then I'm prescribing less weight towards the likelihood. Here, because N is quite a lot bigger than A and B, as I increase N, we are actually going to increase the weight which we give to the maximum likelihood estimate. So it's actually a positive function of N. So you can see here that how the posterior mean actually is related to the prior mean and the maximum likelihood estimate, and how it depends on the parameters A, B, and N. As I increase A and B, then that's actually giving more weight to the prior, because essentially what's happening when I'm increasing A and B is I'm making the prior more and more peaked. And as I increase N, that makes the likelihood more and more peaked and actually decreases the value of likelihood across a lot of the range of theta here. So that actually makes the likelihood that much more important than the prior distribution. So then I weight more towards the maximum likelihood estimate.